How precisely is a Hall sensor actually measuring? We are explaining its limits, and we are checking out interference from a magnetic field. They are widely used, and they are especially important for electric vehicles. Today we are diving into the fascinating world of Hall sensors, explaining how you can use these clever devices. Stay tuned to find out more about their amazing properties. We were showing in earlier videos how to build an ammeter for high currents applying a Hall sensor. Thanks to the galvanic isolation of the sensor, we are safe and we don't need to disconnect or change the power line. Today we would like to answer fundamental questions around these devices. How precisely can you measure with Hall sensors? How quickly can you measure? Are measurement results distorted by a magnetic field? Can you increase its sensitivity? This video is sponsored by PCBWay, our trusted maker. Thanks to their experts, we are always getting great support for our projects. Be sure to check out PCBWay's community platform and these cool projects. And you will find lots of definitely interesting offers on the company's website. Take the easy way with PCBWay. The accuracy of a measuring device applies within its rated range, which is ±100 amps in our example. The nominal output voltage is in the range of 2.5 ± 0.625 volts. The sensor's characteristic is a straight, or at least an almost straight line, as we will see in a minute. The datasheet is also specifying an extended input measured range as ±150 amps. However, outside the rated range, the characteristic is deviating from a straight line. I'm exaggerating this in the diagram to show the saturation effect. According to the datasheet, the rated accuracy of our sensor is 1%, meaning the maximum deviation between measured and actual current can be up to 1 ampere. It's corresponding to an output voltage deviation of 6.5 millivolts. This measurement error can be eliminated by calibration. In other words, you are correcting with the known result of a test measurement. We can use the sensor in the extended range up to 150 amps, but its accuracy is getting worse then. We can't see it, but examining it very closely, we find that the characteristic is not exactly straight within the rated range. Its linearity is given as 0.1%, which actually means the deviation from an ideal straight line. To be precise, its maximum slope deviation is 0.1%. So, if you calibrate out its absolute deviation, the accuracy is getting better than 0.1%. That's remarkable, isn't it? This value is telling us that the sensor output load needs to be minimum 10 kilo-ohm. According to Ohm's law, that's only 250 microamperes at 2.5 volts output. Not enough to drive a typical display instrument drawing 1 milliampere at full scale. High impedance inputs of operational amplifiers or AD converters are ideal for this purpose. The maximum zero offset of 15 millivolts is corresponding to approximately 2% deviation. You can also compensate it by calibration. Applying a differential measurement, we can eliminate the zero offset drift using the reference voltage output. In this way, we are getting rid of the 2.5 volt bias and the output is directly proportional to the measured current. The same principle applies with 2 AD converters instead of 1. In this case, the difference is computed in the processor code. The datasheet is just saying DC for direct current instead of telling us the bandwidth. Okay, let's estimate this from the so-called response time, which is less than 3 microseconds. That means if the measured current is jumping to a higher level, then the output signal is reaching its corresponding level 3 microseconds later. You could use the sensor for sampling an alternating current, as long as its period is greater than 6 microseconds. This is corresponding to a frequency of 166 kHz. Not bad, isn't it? Now we're going to a milliseconds timescale instead of microseconds. This is the voltage in a 50 Hz power grid. One period is 20 milliseconds. A consumer's current could be sampled more than 6,000 times per period with that sensor, sufficient for analyzing phase shift and spikes. Just as a side note, we could connect an oscilloscope directly to the sensor to analyze the current flow. A Hall sensor is measuring indirectly via the current's magnetic field, so it seems obvious a magnetic field can interfere. The experiment with a strong neodymium magnet is giving us an estimate whether this is a critical issue. Surprisingly, I can hardly produce any deviation with the magnet, even if I get very close to the sensor. In that experiment, the deviation caused is a single-digit percentage only. Nevertheless, don't place the sensor near devices generating magnetic fields. Better keep it at least 10 centimeters away from electric motors, relays and the like. Now I'm telling you a trick to increase the measurement sensitivity. Looping several turns through the sensor is increasing the output signal. But be careful. It depends not only on the number of turns, but also on the diameter. A smaller diameter is producing a stronger signal than a large one. So you need to recalibrate, because the sensitivity doesn't just increase by a factor being the number of turns. We will explain the physics behind in another video, but an immediate takeaway from this is the following. The cable should be straight at the measuring point, because loops and bends could cause measurement deviation. The uncalibrated accuracy of Hall sensors is sufficient for many applications. But as explained, it can be improved significantly. A response time in the microsecond range is pretty fast, but there are models that even work in the nanosecond range. Keep magnetic fields away and take care the cable you want to measure is straight. My promised test in the car will follow soon. It was just too cold outside for me so far. Now stay tuned and don't forget to support the channel. See you soon in the coming episodes.